Okay, welcome to Workshop 9. So today we're looking at the last set of classifiers, all of which we've seen in some form before, though perhaps not in this particular context. So we're going to be looking at k nearest neighbours for classification. You remember that we use that for imputation. And imputation, of course, is actually quite similar to a prediction problem or a classification problem if you're imputing a class, right? So it's natural to use k nearest neighbours for classification or for prediction. We'll also be looking at trees and forests. They adapt readily to the classification context, and also neural networks. So we're going to start by reloading the data from on the glass data. You remember that this was quite tricky to classify, and it's quite small as a data set. So we have a large number of measures of different elements and the different classes, and you'll remember that the classes are quite imbalanced as well. So we're going to try fitting a bunch of different models to this. So we're going to fit a nearest neighbour model, a decision tree, a random forest, and a neural network. So to fit a nearest neighbour, we're going to go mode equals classification. And then we're just going to specify the number of neighbours that we want. So I'm going to start with maybe 5. And then we're going to fit our outcome variable type in terms of the all other predictors on the training data. Okay, so we're going to have class dot knn. Okay, and you'll see here that that this engine requires some package installs. So we need the k nearest neighbour package first. So I'm going to install that. You remember I don't type install packages in my Markdown file because this is a one-off operation, right? So we only want to do it once, so we execute it in the console. So we're going to install the package that it's asking for, which is kknn, and it'll go away and do that work for us. And there we go. Right, so now if I execute it, it should function. Perfect. Okay. And so we're now going to also fit a classification tree. So an R part. So we're going to be using a decision tree. And mode equals classification. We'll perhaps just use the default cost complexity, and we might change that later. Okay, and then perhaps a forest. Remember, with the random forest, we're going to be using the random forest engine. You can use, so the default is Ranger, you can use that if you'd like. You have to install it, is the only thing. And we'll also fit a neural network with MLP. So again, mode is going to be classification. And we'll have to specify the number of hidden nodes. So the number of hidden units. So in this case, we've got, I think we've just got, 9 numeric predictors. So I think we can probably just use, say, 4 or 5 hidden units. Is probably a good starting point. And then we will fit that. We may have to, of course, assess convergence and so on and so forth. Right, so we'll run that one as well. So now we have all of our models fit. We can then evaluate the performance and potentially tune them. So let's augment with the glass.test data, and of course, because I want to do this all at once, I'm going to bind them up into a list. And then we're going to just call this then I'm just going to do them all one by one. So we're going to have RP, RF, you can see that a lot of this is boilerplate, and of course there are ways to operate. We're running the same operation, so here we're running fit on a bunch of different things, and here we're running augment on the same bunch of different things. So we could, if we set the list object up initially with the output with our specification, then we could use the map function in per to iterate over that list and run the fit function, and then we could again use the map function in per to do the augmentation. So perhaps I might show you that for the for when we do the next example. So what I'm doing here is I'm binding the output together. So I'm using augment. So augment is going to produce a data frame. It'll have the same columns, of course. And so we're going to get a data frame for KNN, a data frame for RP, a data frame for RF, and a data frame for NN. And I've popped them all in a list, which I can then supply to bind rows with an identifier. The identifier column is just going to take the names of that list and put them in the column for model. Okay, so the output from this will be our predictions. Okay, so if we have a look at glass.pred, then we have one row per prediction for the KNN model, and then for the RP model, for the RF model, and the NN model. And of course we have the same information from each. So we've got the individual predictions, and we've got the predicted class. And so now we can group by our model. So this is all on a data frame, and then we can run our accuracy function. So truth is going to be our type, and our estimate is going to be our class prediction. Okay, so you can see here that it seems that the decision tree and KNN are doing best on these data, with the forest just a little bit behind. Now these are of course completely untuned, and we may want to mess about and see if we can do better. Now I'm not sure what happens if we run the confusion matrix. Can we run the confusion matrix if we have a grouped data frame? I'm not sure. Let's see what happens. This may not function because of course the confusion matrix is going to be returning a matrix. It does. So it produces a confusion matrix. I don't know if we can then map that and convert it to a data frame. So let's try. No, so it doesn't have a as Tipple maybe? No. We could try as data frame perhaps. They're not named. Let's see. No, so it can't coerce them. There's probably a way to do it, but in the meantime, in fact, what I'm going to do is I'm going to group split. And then run map. And then run the confusion matrix with truth equals type estimate. Let's see if that works. There we go. So what I've done here is, so the group split allows you to actually take your grouped data frame and actually split it into a list. So you can see here that I end up with a list of data frames, and I've got 4 separate data frames. Okay, here they all are there. 1, 2, 3, 4, and then because I've got a list of data frames, I can supply them to map. So map just iterates over a list and applies the conf_mat function to each of the data frames in turn, where the truth is type and the estimate is predict.class. So we get our predictions all at once. So we can have a quick look at these. Let's have a look and see how they're doing. So they're all, so you can see here that the second one is not ideal. The second one would be the RP, I'm guessing. So even though that's actually a really good, it's one of the better predictions, it's actually predicting really poorly in that everything has been predicted to be a window building. So this is actually a really awful classifier, but it's doing the best because these data are imbalanced. And the others are actually doing slightly better. That can't be right. The order must be different, right? Let's have a look. I'm not sure if you can get it to split while naming the variables. So you can see that the first one is RP. The first one is KNN. The second one is NN. So NN is doing poorly. The third one is RF, and the fourth one is RP. I'm not sure if you can actually name them with group split. It'd be nice to name those data frames, wouldn't it? I guess what we could do, if we wanted to do this a little bit nicer, what we could do is we could say have our prediction as a list, and because it's a list and it's named, right, if we just have a look at what that looks like, you can see it's just the list that we had before, but this time it's actually named. So we've actually got the names, and then we could run that and would get them named. So now we can see that the model that was performing poorly was the neural network. And the neural network here is just assigning everything to the window building class. Okay, so let's perhaps redo this using this format, because I think this is a little bit nicer. So instead of binding rows and then doing everything, we'll instead keep everything as a list and bind it up at the end. So that's confusion matrices. And then what we could do is we can just bind rows, group by model, and then run accuracy. Get the overall accuracy. I think that's a little bit nicer way of doing it. It's less code, mostly because when we're computing the confusion matrices, because they are not returning a data frame directly, they're a bit awkward to use inside a data frame. Okay, they're instead producing a table, and tables and data frames don't necessarily marry up all that well. I'm sure there is a way to convert the confusion matrix to a data frame, because that would be useful for things like charting. But this seems like a more natural way to do it. And the other reason why this is more natural is that it extends very easily. So if we'd already had the the objects glass.knn, glass.rp, and glass.rf in a list, then we could have in fact done the augment all at once. So if we go like this, so our model list is a list of 4 objects, so you've got your KNN and so on and so forth, then we could have actually said, so I'll perhaps put this down here as an alternate. Then we could just go take our model list and just map it with the augment function with new data set to class.test, and that would give us the same thing, right? We've got the same confusion matrices and the same accuracies. Okay, so less things to type, right? And you can sort of see how this is going to extend naturally. So the only thing that actually needs to change is the model specification. So if we'd actually started by putting each of the model specifications in a list, then we could have run fit across that list using map all at once in one go. We've already got the list here, we don't have to construct it again, so we'd have a very small number of lines of code, essentially just taking care of that repetitiveness. Okay. Right, we might want to mess about here a little bit, so let's see if we can tune things just a little. So what we're going to do is let's see if we can maybe get a better neural network and perhaps a better nearest neighbour, or a similar nearest neighbour. I suspect we won't be able to do much better than that, but we could mess about with it a little bit. So let's see if we can improve these two, or we can at least change them a bit. Okay, so let's perhaps make a second one where we use one nearest neighbour, and I'm just going to fit everything at once in order to get an idea. We'll just run accuracy directly. Just to see how I do. Okay, so the accuracy is 0.833. Before we had 0.888, so 5 was better. Try 3. Okay, it's kind of similar. We're not getting better or worse really. What if we use more neighbours? Okay, so eventually, we get some slightly different performance, but 5 seems to actually be the sweet spot here. What about for the neural net? So for a start, I want to know, are we actually reaching convergence? I guess we could set the seed too, couldn't we? Because otherwise we're not going to get necessarily the same answer twice. So let's actually have a look here, and so the first thing I want to know is, am I going to get the same answer when I run it again? Okay, so I've got better improvement just by changing the random seed, which suggests that maybe we're not actually reaching convergence here. Let's check by pulling out the convergence. Remember, the convergence is stored in the model fit. Okay, we actually haven't reached convergence. You remember from the help for NNet. If you look at the value object, the thing that it returns to you, it'll return convergence 1 if the maximum number of iterations was reached, otherwise 0. So we're not actually converging here. So I'm going to increase the number of epochs, and then we have reached convergence. Now it may not do as well when we've whoops, I don't need the convergence there, do I? Okay, so 0.87. So we're getting a little bit better. We could mess about with the number of hidden units. Let's try a few less, see what happens. Okay, we're performing worse. Let's try a few more. Performing worse again. Have we converged? Yes. Okay. What about even more? Okay. This is probably too many hidden units in this case. Remember the size of the training data is actually quite small. We've only got 160 observations and we've got 9 input variables. So if we have 10 hidden units, then you've got 10 times 10 weights just to get to the first hidden unit, and then you've got another 10 weights on the output. So you've got a large number of weights here, sort of 110, 111 weights I think all up, and we've only got 160 observations, so it's going to be very hard to get good estimates of these weights. So let's skip back to 5 hidden units, which seem to be about the best. Remember to set the seed. Okay. We could also mess about with the penalty for the weight decay. See what happens when we mess about with that. We're getting about the same. Let's check convergence. Yep, we've got convergence. So there we go. We've done slightly better. Whether we can get better than 89%, I don't know. See how well you do. Have a play around. Do a bit of tuning, and see whether you can improve things from that. So which model performs the best? The decision tree and K nearest neighbors. Okay. So this next one now is a new example where we're just going to try classification on some images. So these are photos taken of the Avila Bible, which is a Latin copy of the Bible produced during the 12th century, and there's a number of different copyists or scribes that have written this Bible. So the Bible, of course, was copied from an earlier sets of manuscripts, and by looking at the way the writing was set up, you can identify different potential copyists. And we've got a large number of measures here that describe different elements of the page, essentially. So you've got the intercolumn distance, so the distance between columns of text on the page. So different scribes use different amounts of space. You've got your upper margin, your lower margin, how much of the column is exploited, so how much ink there is in a particular column. Some scribes use more ink than others. Number of rows on the page, the average ratio of the width to height of the characters that we used, and so on, right? We've got interline spacing. We've got the proportion of each row filled with ink, and we've got the number of peaks in the ink density across the row. So essentially that counts the vertical bars in the letters. So the letter L and T, for example, would be little spikes because you've got a large ink density vertically as you whenever you hit a letter with an up or a down vertical line in it. Whereas the lowercase letters will have less vertical ink density as you go across the row. Obviously, this wouldn't have been written in English, right? And may not have been using these standard characters, the characters that we use today, necessarily. They may have looked quite different. And then we've, of course, got the scribe. So which copyist or scribe it is that has written that page, or that has produced that page. And the goal is to assign sections of text to the correct scribe. Okay, so we've had some people who know a lot about this manually classify some of the pages, identify potential scribes, and so now we want to use computing to classify the rest. Obviously it's quite a time-consuming exercise to evaluate which scribe it's likely to be, and potentially there's room for the human classifier to get things wrong, right? So having essentially a machine learning algorithm that assigns the scribe for us is sort of an independent check in some regards. It's not fully independent, of course, because we're training it on the data that the humans have produced. Okay, so let's have a look at it. So we have all of these variables. So we've got a large number of rows, large number of pages. Okay, and we've got all of these measures which have all been normalized for us already by the looks. And then we've got the scribe. So the goal is predicting the scribe given these other pieces of information. And then we've got the test set, which again is an independent test set, so we've got the answer here as well. Okay, so let's start by exploring the data. So what I'm going to use is assess the relationship between each variable and the target scribe. So because they're all numeric predictors, what I'm going to do is I'm going to pivot this longer. So we have a name column for which variable I'm looking at, and then the value column for the value that the variable takes, and then the scribe column. And then I can shoot it at ggplot and use faceting to have a look at things. Right, so we're going to take our training data, and we are going to pivot it longer. Where we're going to do everything except the scribe column, and our names are going to go to the name column, and the values to a value column. So this is actually the default. I could have actually left the names to and the values to out here. Right, so that's going to give me which scribe it is, which measure it is, and what the value the measure takes. And the idea is I can then feed that into ggplot and perhaps do some density plots of the value coloured by the scribe, and then facet by the name. Right, so that I get some plots like this. Okay, so I immediately note that the range on these, some of them anyway, is very, very large. So perhaps these haven't been normalized as much as I thought. So let's switch the scales to free x to free, just so we get okay, here we go. So it seems that some of the variables do have some very large outliers, so we need to be a little bit careful about that, and some of them are quite good for potentially quite good for classifying. So you can see this exploit one, and cruels seem to be quite good. Harder to tell with the others because they're all bunched up a little bit more, but we do have to potentially watch out for these large ones, particularly in this measure and in these measures here. So that's going to be important for when we do things like neural nets, for example. And even if you do like a linear regression, right? These are going to have a lot of leverage in your multinomial regression. These are going to have a lot of leverage in that regression. So we're going to have to be quite careful about things. Okay, so what else might we do? Well, I want to get a little bit of a feel for how many are very strange. So I think I might just look at this variable here, the upmar variable, and just find out how many are bigger than, say, 10. So let's look at UpMar. So we'll go, perhaps actually we'll just take our training data and we'll just filter where UpMar is bigger than 10, say. Okay, so we only have 18 rows where that happens. And there's only one observation that it's very, very large. Okay, we've got UpMar as 386, so I wonder whether we may... I noticed that it also has LowMar equal to 50, char ratio equal to 53, and if we go back and have a look at this, LowMar equals 50, it's going out to there, char ratio equals 53, it's going out to there. I wonder if it's all been driven by that one observation. Yes, look at that, ILS 83, that's the maximum there. Number of peaks 44, that's the maximum there. Right, so I think we remove this observation from the data. So let's find it. We could just say it's the one with UpMar bigger than 300. Okay, so that's the one we want to remove. So and then I'm just going to repeat the above. I'm going to repeat the same graph that I did above on this clean data set. To get a better feel for things. That looks better. So there's still some extreme observations in UpMar and in weight, but nowhere near as bad as before. Also in num_row, but there seems to be a number of them. We've got a wee peak there. I guess we could go back and have a look at let's go back and have a look at UpMar bigger than 10. So there's 17 of them. So there is one with it 43, but it doesn't seem all that extreme for the other measures. I guess weight is 13. What's that? Yeah, so it is still, there's one with it that's a little bit extreme still, so we might potentially consider removing that one. I'm also going to run the same code on the test set, just to test whether there might be very odd observations there as well. No, that's looking pretty reasonable, isn't it? Again, we do have some outliers, but it's not massively different. So I'm okay with that. So right, so I'm going to fit a range of models, and I'm going to do it in a way that produces lists of models, just so that the boilerplate stuff I can just iterate over with map. Now, this is This is not something that you have to do for your assignments or anything like that. It's just a more efficient way of doing things. Okay, and there's other packages that can help you with this as well. So, for example, the workflow package in Tidy Models can help with the sort of the range of things that we want to do. Now, what I notice is that some of the variables are quite large, but not too bad, are they? They're mostly all on the same scale. Every now and then we've got a big one, but it's only 1 or 2. I don't think we'll need to scale this. I think this will be okay to use as it is. But it's something that we could potentially explore. So we would expect, for example, that the one with the very large up margins will still be, they're still quite extreme. And potentially you might want to get rid of them still. I mean, there's only a handful of them, isn't there? There was only 17, I think, with bigger than margin, then upmar being 10. So you could potentially get rid of them if you want. It's not as if you're short of data. We've got 6,009, almost 7,000 observations. So I'm going to fit a range of models. So let's have a look at what they could be. So I'm going to fit a. So for a start, we can tell that we're not going to fit a logistic regression, because of course we've got too many classes. Logistic regression only applies to 2. But we could fit LDA, we could fit KDA, but of course KDA, you remember, can only take 3. So we'd have to either choose 3 variables or use some feature reduction technique. So for example, Alex, the other day, we were chatting and he mentioned, could you do a PCA on these first? So some of you I know would be taking 161323, multivariate analysis, and so you'll know all about principal components analysis for essentially for reducing the dimension of data. So that's an ideal thing to be doing prior to doing a KDA. You could just use the first 3 principal components computed across these things. So yes, that's definitely something you can do. If you're interested, then the recipes package has a step PCA, okay, for you. So you remember we used the recipes package for doing things like normalization. It can do the PCA thing for you. You could also potentially use something like a PCA adapted to the classification context. So in 323, those of you who have taken 323, if you haven't, don't worry about it, right? This is extra for expert stuff. But in 323, for example, you look at principal components regression, where essentially you're choosing the axes such that they correlate with the outcome variable in some way. And you can do there's similar types of things for choosing the principal component axes such that they correlate or they help separate the classes. So there's definitely ways to do that. And in a sense, that's kind of what LDA does as well. Okay. Right, so we're going to do a bunch of models. So I'm going to fit a linear discriminant. What else? What other models? Let's make a list of models. So we're going to have LDA. What else? I'm not going to do KDA just because it's only going to have 3 predictors, and I want to be able to use all of my predictors all the time because I want a common fitting function. But I could do naive Bayes. With the naive Bayes engine. What else? I could do a multinomial regression. I could do k nearest neighbors. Classification. got a big data set. I might try 10 neighbours. We could do a decision tree. I can do probably quite a complex one. I've got lots and lots of data. I'll do a forest. And a neural network. Got quite a bit of data, so I could have many hidden units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've got 10 predictors. So we'll start with 5. And we'll just give it a number of 1,000 iterations, just so we don't have to think about it. Okay, so these are all my models. All set up. So if I have a look at my models, then you can see that I've got a bunch of things set up. So now I'm going to fit them. So I'm going to take my models and I'm going to map the fitting object, and the formula is going to be outcome variable, which is our scribe in terms of everything, and our data is going to be our training data. Our clean training data. Okay. So no engines were loaded for Descrim linear. Please load a parsnip extension package that provides one. So I'm going to use library Descrim. Okay. And now we're going across and mapping our model fit. So this is fitting all the models. I probably should have set the seed before I did this. It'll be taking a wee while because this is a big data set, and I'm just going to refit it again with a set seed just so that I can reproduce it. And you can reproduce it if you want to do the same thing, of course. So fits now will be a list of 7 because we've got our 7 objects. The names, of course, will be the same as we had before, right? And you will get lots of guff out of here. So there's our tree. Okay, here's our naive Bayes. It's all this output here. All right, we've got lots and lots of output for the naive Bayes because we're fitting a kernel density for each scribe within each variable, and there's lots of scribes. Okay, so now that we've got our model fits, we can evaluate the predictive performance. So because everything's in a list, I could do the augmentation with our new data equal to our test data, right? And it would automatically give me a bunch of data frames, one for each model, right? And each of those data frames has got our prediction information in it. Okay, so this is going to be our preds. Right, so these are our predictions, and then we can evaluate them. And produce our confusion matrices. So immediately here, when I look at this, I notice that Scribe A has been much more proficient, has written a whole heap more than any of the other scribes. So this is a highly imbalanced data set. And you can see that, that the models aren't doing great. So LDA, for example, tends to be assigning everything, many of the observations to Scribe A, which is the largest class. This one here is doing a little bit better. We've got a bit better down the diagonal. We're missing out, so we're getting F wrong quite a lot in the naive Bayes. Is the multinomial. K nearest neighbours. And the decision tree, that seems to be doing really nicely. Just judging by the number on the off diagonal there. The forest is also doing extremely well. Very nicely. Neural network's not doing terribly flash. So based on this, I'm guessing that the neural network's going to be doing, so we can compute our prediction data frames and confusion matrices. I'm guessing that the forest is going to be the best. Let's have a look. So let's just compute accuracy. Right, so what we could do is take our predictions, bind them together, group by the model, and compute accuracy. Truth is going to be the scribe, and the prediction estimate is going to be our predicted class. Okay, and as I suspected, the random forest is by far the best, and the decision tree is second best. Now, there's been no tuning here. We could, of course, tune, although I would say, looking at the clear difference in performance here, I suspect that I would be quite happy to drop LDA out, and maybe MN and NN, and just not bother tuning those. I mean, I may get, there's a big gap to cover, and you'll want to apply time to the models that you think are actually going to make a difference. I would tune the very simple models first, like K and N. Naive Bayes might be worth looking at. There's not a lot of tuning I can do there. The assumption, of course, is independence, so I could look at independence just by, for example, going back up to the graphical analysis here. I could look at combinations of these. So have a look at char ratio versus accruals, do a pairs plot, say GG pairs, for example, color it by the scribe, and just see whether independence holds. Okay, let's have a quick peek maybe. So based on this, the random forest is clearly the best. It's not even close. But we've done no tuning. So what about naive Bayes? It's nowhere near as good as the forest, but still not too terrible. There's not much we can tune. We could potentially switch to Gaussians instead of densities. But does independence of these things even make sense? And you can get a feel, just based on what the data are. My initial impression is that independence probably doesn't make sense. because I know I've got some measures for ink density across the page, and I've also got measures for how wide the margins are. And of course, if the margins are bigger, then the ink density will be lower, right? Because you just can't have as much ink on the page if your margins are smaller. So those things are likely correlated. So I'm guessing that things are correlated. And we could just have a quick peek. So let's use our clean training data and just have a look at a couple of variables. So perhaps we'll just try those, the first couple. Where's our... So let's look at ICD. Y equals upmar, and then we just color by Scribe, just to get a feel for what's going on. If you get this strange error, it's because you're using a pipe instead of a plus. It took me a wee while to figure that one out. Okay, so this actually looks reasonably independent, probably. Yeah, you've just got a big pool of data here. There doesn't seem to be high correlation between those two, but we could just try some others. So, is the upper margin correlated with the lower margin, perhaps? Not strongly so. Hard to tell what's going in this group, but there we go. What about some of the others? Okay, so there's some negative correlation there, but it's not super strong. So, you can explore the potential correlation between pairs of variables at least. Now, there could, of course, be correlation across 3 variables or 4 variables or what have you. But nonetheless, it'll give you a feel for whether naive Bayes should do well. You could automate this with a GG pairs, so from the GGLI library, we've got GG pairs. Color by Scribe. Lots of warnings here, but that's okay. We just do an exploratory data analysis. We just want to have a feel. We don't care if we get things, if our plot's great or average. Okay, so I'm just looking down here. So there's correlation here and here. That's fairly strong, but actually independence isn't too bad for a number of these. There's probably some correlation here as well. So yeah, there's correlation between the char ratio and CRILS, and also between ILS and CRILS. I seem to remember that some of these variables are just computed based on the other ones, so that's probably why that is. But overall, we should expect naive Bayes to actually not do too badly, and it didn't do too badly, but it wasn't great. Okay, but I don't think there's much scope for improving things. So my guess is that the random forest is probably going to be the best. If instead we want of classification performance, the goal was to understand how the scribes differ, which model would we prefer? So this is quite a different question, isn't it? So when we're doing classification performance, we don't care, and all that we're interested in is optimizing classification accuracy. We don't care what the underlying model is telling us. Like, we don't need to be able to say, well, this is the feature that distinguishes the scribe, or this is the feature that this scribe uses bigger margins than the other scribes, or whatever. We don't care about that. All we care about is some combination of all this stuff can be put into this magic black box, and it tells us which scribe it is. Okay. But what if we did want to know information about things? Then we'd want to use a model that allows us to say things about inference, essentially, right? So essentially it's the difference between prediction and inference. So classification performance is predictive performance of the model, whereas if we want to explain things, then we're talking about inference. So we want to be inferring which variables are telling us about the scribes and which variables aren't. Okay? And to do that, we need a model that we can interrogate and understand. And the forest is not great for that. Okay? Because the forest, you can tell which variables are most important, but you can't tell what values of the variables or what ranges of the variables are associated with individual scribes very easily from a forest. But we can, of course, do that from some of the other models. So, for example, if you had a multinomial regression, that is specifically giving you a linear predictor for each scribe, basically, or at least for all of the scribes except one, right? And you can infer things about the other scribe from that. And that will tell us the contribution of each of the variables to each of the scribes. Similarly, a decision tree will tell us something about the scribes because you can use the shape of the tree to tell you information about the scribes. Okay, so this is an inference problem. So we'd like to use a model that we can interrogate for inference purposes. This differs from prediction, where we really only care about did you get the answer right, and not about can you explain what is going on. Right, so it's basically, if you're looking at inference, then you want transparency. If you're looking at prediction, then a black box is fine. And sometimes you want both, right? So sometimes you do actually want to favor a transparent model over one that's opaque. And you can get some transparency from things like a forest, because you can do things like look at what the average tree looks like, or a representative tree, or perhaps a number of representative trees. So you can take all the trees in your forest, and you can basically use some distance measures to find out which trees are similar, and then choose a representative from these similar trees. Essentially what you end up doing is clustering the trees in your forest. We'll look at clustering next week using some distance metric, and then you basically just sort of pick out some trees from each of those clusters, and those trees then sort of are your representatives of the forest. Of course, if we've just got one tree, then we can just look at the tree, right? So we might choose the decision tree in this instance, as it gives the second best performance and is transparent to interrogation. Right, so we could grab our tree, so we could grab our fits, and it's the tree, so there it is there. Right, and we could then extract the fitted object from there, and we could do our usual plotting of the tree, for example. Let's see what we get. Okay, so it's a very, very big tree, but you can see what the important variables are at the top, and then we would need to explore it in better detail and get a much better looking plot, won't we? Let's try compress equals true. We'll lower the size of the text. see if we can get something looking a bit better. Okay, we're getting something. And you can see here, so what I immediately notice is that A and F seem to pair together down the end of the branches here. So to investigate this further, probably what I would do is I would try and get I would start looking for other packages for plotting the tree, because it's a very chunky tree. Maybe I'll try and simplify it a bit. So perhaps use a lower complexity and check that I still get a reasonable classification, and then look at plotting that, so it'll reduce a little bit of the complexity down here in the tree. Plus I would be looking at something that is just produces nicer plots of the tree. So there's a whole heap of packages available for plotting trees. Not all of them do this compression thing. So this compression thing is basically a consequence of it's trying to capture how much improvement you get from each split. And so these splits down the bottom here, you don't get all that much improvement from, whereas these ones at the top you get a lot of improvement. So that's what the sort of the vertical height here, the idea behind that is. But that might help you then identify the combination of things that are features of a particular scribe. And in particular, you immediately see that scribes A and F obviously have fairly similar have a very similar set of writing, because they writing characteristics, because they tend to come down similar branches on the tree. Okay, so that's what I would be looking at from there. You could probably get some information just by spitting out the tree fit as well. Okay, so if you look at for example this, right, it's mostly A. You're 96% chance of being an A and a very small percent chance of being an, I think this is probably an F, and you can then see the characteristics that give rise to that. Okay, so the difference between A and F here are the exploit. Okay, so F's range of exploit tends to be less than 0.96, whereas A's tends to be bigger than or equal to 0.96. Okay, and so forth. Right, you can get other information from here. Okay, so that's what I would be doing if I wanted to explain things. You might also choose the multinomial regression if the multinomial regression was any good. I don't remember exactly how good that was. It was pretty terrible. Okay, but of course, again, untuned. So maybe we can do a little bit better out of this, and that of course will help explain what might be going on. You do get a little bit of explanation out of naive Bayes, in that essentially what we're fitting is a univariate distribution by a scribe within each variable. So you do get sort of rankings of the variables along of the scribes along each of the independent axes. But of course you also get that just by charting them, right? We get that from the chart that we had up the top here. Okay, and you can see this, because there's quite a lot of overlap, that doesn't necessarily tell you all that much past what the charts are telling you, whereas the tree is telling us how all these variables combine together and interact with each other. Okay.